Okay, what do we think? I'm asking about the rate of change, though. What kind of rate of change is that? Constant, but it's a specific constant rate of change. So normally we call that the average rate of change, right? So the average rate of change, what is the constant rate that achieves the same change in y as the function actually does, right? So there's this change in y function achieves. So you want the constant rate that achieves that same change in y. That's what we mean by average rate of change. Okay, so what do we do next? Let's see here. So we want to define the formula for A. So here's the thing about this. It's not going to take us a month to do the reverse process because we develop a lot of tools along the way that are very helpful. So we want to look at, say, this is any interval now. This isn't necessarily the second interval. Think about this as any interval. And this is the point x, comma. We use capital A to be our approximate. X, comma, capital A of x. Okay? And so we want to use what we've learned to write a definition for capital A of x, thinking about that being any point within any interval. So this could be any interval, so this is just a typical interval now, not necessarily the second. How would you write, basically, given x, how would you write the y coordinate of that point? I've actually done this several times. It's a little different now because it's going to be based on this known function f, which is our volume of the sphere. So can we write the definition for A? So this may take some putting your ideas together, right? This isn't going to be something that you just do lickety split, but you may think of what is the general form of it. We've seen that before. So what's the overall structure of it? And then once you get the overall structure of what A would be, then you start working on the details. How can you get the different bits and pieces of it using things that we've learned? All right, so I want to give you some time to see what you guys come up with. Okay, we can do this. So let me just tell you, we can write the whole function just by focusing on one interval. All right, so it's not going to be a piecewise function. Okay, it's not going to be a piecewise function. We can just, if we just write the rule for any typical piece, we can actually write the whole function. Okay, so it's not piecewise. It's not do the first one, then do the second one, do the third one. So if you just think of this interval as an arbitrary interval, it could be the second, third, eighth, whatever interval. You can just focus on this one interval and write this. So first decide what the overall structure will be, and then work on the pieces, and I'll come along and see what your progress is. Get all these coordinate pairs. So here's an arbitrary coordinate pair, x, a of x. How would you define the y coordinate of that, and thus the y coordinate of all those points in this interval, right? Just focus on that one segment. Anyone think they have it? Okay, it's not. It's okay. So you got to get away from it. It's not the summation that when we had the rate and we had to do the summation thing. It's not that. Okay, just focus on this. How would you write that one segment? How would you write that one? How do we define one segment? What did we talk about? We got some of the elements, but the structure is off. Okay, so remember in a piecewise function, y final equals? That's like y final, right? Equals? bit sad. Y initial plus dy, right? Y initial plus the change in y. Right? This was how we did linear functions, right? This is our linear function. And so what is y initial? Y initial is? All right, and so for this interval, it's f of 0.4, but what would it be for any interval? F of left x, right? So there's our y initial. And now the change in y. How do we then get the change in y? No, h is the change in x, right? You know, we want to use constant rate of change to get this, right? So the dy is m, what was it? M dx, right? M dx. Dx is, let's do dx, that's the easier part first. Dx is? So it's whatever we're at, the x. The dx is this right here. X minus left x. So y final equals y initial plus change in y. Now we've got left x, this really helpful tool that we can use. So y initial is the function evaluated at the left side of the current interval. And then dx is how far we've gone into the current interval, so x minus left of x. And then finally, m is? So where does that constant rate come from? Yeah? Okay, so the reason that doesn't, what is f of x? F of x is this right here. So maybe I might not have looked at some of your rate expressions close enough, but that's the right idea. But then if you do f of x minus f of left of x, you get this rate, which is not the rate we want, right? We want the rate that is uses the points at the end of the interval. So it's like it uses this final y value that you really haven't gotten to yet. Okay, so did you guys? Maybe I didn't look at your rate close enough. Did you do f of x minus f of left of x? Okay, do you see that that's not right? Because f of x, this y value, the y value of this point is f of x. So if you do f of x minus f of left of x, you get this there. And we want this one. Yeah, Jesus. Okay, so we want, so tell me, so the f of, okay. So that's that y value. Then, keep going. Minus f of left x. So that's the change in y right there, right? That's the change in y in the current interval. Then? And what's that? Which is? Just h, right? Yeah, you're right. You're right. Okay, so y final is y initial plus change in y. Y initial is f of left of x. Change in x is however far we're into the current interval, x minus left of x. And then we can get m. So this is the key here, that we have to, if we're going to use the rate is determined by the endpoints of the interval, not the current value of x. So we need f of left of x. I've got a better version of this here on the screen. So that's easier to read. Okay. Does it make sense? Do you see how that's applies what we did earlier in the semester? See that? Okay. So now I want you to, so we got our formula for A. For A was the approximate rate of change. And now on the left, I want you to sketch R associated with A when you've got 0.4. So you're only gonna, I think you only have 3 intervals that you got to. this A for h of 1.4, or say h of 0.4. Now, are you going to use the formula for left of x to do this? Remember that we built left of x, you're going to need that? You're going to be cranking out left of x's? Why not? What's that? So for this particular, what I'm showing you now for h of 0.4 and 3 intervals like that, I want you to sketch the r function. So my question is, to do that, do you need left x and the formula for left x, cranking out what left x's are using a formula? Because? Right, so what are the different left x's that you'll have? 0 for the first interval, 0.4 for the second interval, and 0.8 for the third. So we know what they are, right? Because I've told you that h is 0.4. You just know for the first interval it's going to be 0, for the second interval it's 0.4, third interval is 0.8. Okay. And what is the function f? What was this all about in the first place? Of what? What was this all about? But what context are we in? What is the function f? What's that? Volume of a sphere, right? So you have the function f. You know what your left will be. You'll have 0, 0.4, 0.8. So we want to sketch the approximate. Anybody get a number for the first rate? Anybody else get that? You guys got that too? Okay, so I'll just write that down. So for the first, I'll call it M1. The first rate of change is 0.67. So if you can get this 0.67, you know you're doing it right. You're on the right track. Karen, what'd you get for the second rate? Close to 2? 1.9 or 2.1 or exactly 2? Okay, you estimated from what? Is it exactly 2? 4.69? 4.375. Those are too far apart. What'd you guys get at that table? Second rate. Okay, so 2 tables have gotten 4.69. Did you get that? Noel got that too. So I think that sounds right. Okay, and then M3? So then so now we're building these, right, these constant rates over each interval. What would that then approximate rate function look like? Good? Alright, so you guys all got the right idea here? It's going to be our step function, right? What did we get for the third one? 12.73. Is that what you got, Brittany? Remember? You forgot what you got. Did you guys get something? 12.73? And then I saw good sketches, so let's put that up. So you can see how, and what's they? Okay, well, what about if when I mean, even when I was just showing just the accumulation? So yeah, so she's talking about how the you can see for any given value of x, you can see where the accumulation is at and the rate is at the same time. Yeah, that's good. But what if I was just showing accumulation? That's the same question. Why show it this way instead of just the finish? Okay, so a graph is what? A set of points, right? It's a set of infinitely many points. And so that's one thing about this, showing it this way emphasizes that we get one point at a time, right? So there was, imagine there was some point in time when this sphere was growing, right? And we were accumulating volume of the sphere to get up to whatever current value it is. And to do that, we had all the radiuses and volumes along the way to get there, right? So it shows this process of accumulation. Other comments? So what are functions and graphs about? A collection of points that show what? What do they show? So they're a collection of points. But those collection of points are displaying what? What's that? Yeah, covariation, right? Covariation of, in this case, covariation of what? Okay, that would be the right graph. And over here, covariation of? Rate of change of? Yeah, so graphs, there's a set of points that are showing the relationship, the covariant relationship between two quantities, right? And so on the right graph, we're seeing the relationship between radius and volume. On the left graph, radius and rate of change of volume. Okay, and so that's a dynamic process, right? Covariation is a dynamic thing. It's not just a shape sitting on a page, right? It's as one quantity increases, how does the other change? How does the other change, or how is the other generated? So it's the way we want the image we want students to have of graphs is a dynamic covariation of two quantities. That's the main reason why we do this. I want them to see them as a collection of points that are generated showing the relationship of two quantities. And so as you've worked with high school students in your internships, is that what students, the image they have of graphs when they're working with graphs? No, it's like, oh, this is a wire, and if I change the equation this way, it changes the wire this way, right? And this equation is the name of this wire, right? Right, so it's totally different, right? So showing them dynamically is one way to encourage thinking about its quantities that vary together, right? Two quantities that vary together. How are we doing? Okay, let's do one more thing. Where are we at? So, definition of the rate function. So I'm calling this R1. So this, for any given h, so this is for h of 0.4, but for any given h, can you write the rate function? For any given h, not just. Right here? Yeah, we already did it, right? It's this thing right here. It's the rate of change. This rate gives us the rate at any value x. So it's that, we already did it. It's part of the accumulation function. So there's the rate function. so now we want, so how about this rate function? Is it according, so compared to the original volume function, good rate function or not so good? Not so good, right? This is a really kind of a really crude approximation. It's not accurate at all, and you all know how we make how we make it more accurate. What do we do? That's right. So I can do that right here. So every time I make the interval smaller, what happens to the approximate accumulation function? What will happen to that? Yeah, it'll be less daylight, right? Or when you make those intervals smaller, I'll do it here. Ready? There's a smaller. So now the pieces. There's more pieces that are a narrower interval. And then what happens to the approximate rate function? Smaller intervals, more of them. So we think because now it's based on this approximate accumulation function, it's quote unquote more accurate. More accurate to what? Well, if we go smaller even, what do we see? We see a rate function, kind of a continuous rate function start to take form. How about our approximate accumulation function now? I got h is 0.05. How's the approximate rate function? Pretty good? Or accumulation function? We can't see the difference, right? So for our view of this, can't see the difference. There's no daylight, right? But it's still a piecewise linear function according to that definition up there. And if you make h really small, then you see all these constant rates starting to form a smooth curve. And so the question is, what's that curve, right? So this is the actual rate function, which our step function, our rate step function gets closer and closer to as we make h smaller and smaller. So then the question is, what is that? And so we'll pick it up Thursday, but this actually is kind of a dead end for getting that rate function. So when we start on Thursday, bring this handout on Thursday again. We'll start below the line there, and we're actually going to kind of start over with a new approach, a different way of looking at this. Because in terms of getting the actual rate function from this, it's not convenient. It's kind of a dead end. So all right, so marble drop Thursday.